Tonight, we journey back to a time when our planet was nothing more than a churning sea of molten rock and metal, suspended in the darkness of space. 4.5 billion years ago, Earth existed in a state so alien, so utterly hostile to life as we know it, that it challenges our very conception of what a planet can be. This was the Hadean Aeon, named for Hades, the ancient Greek realm of the underworld, and it was during this epoch that our world experienced one of the most extraordinary phases in planetary evolution, a time when the entire surface of Earth was not solid ground, not ocean, not atmosphere as we understand it today, but rather an endless expanse of liquid fire. The story of Earth's lava ocean is not one of destruction, but of creation. It is a tale of transformation on a scale so vast and over periods so immense that human minds struggle to comprehend the sheer magnitude of what unfolded. Yet this molten beginning was not chaos without purpose. Every bubble that rose through that incandescent sea, every current that swirled through those depths of a liquid stone, every moment of cooling and crystallization was laying the foundation for everything that would follow. The continents beneath our feet, the iron core that generates our magnetic field, the very atmosphere we breathe, all trace their origins back to this primordial ocean of fire. To understand how Earth became a lava ocean, we must first travel even further back in time, to the birth of our solar system itself. 4.5 billion years ago, where our sun and planets now orbit in stately procession, there existed only a vast cloud of gas and dust, slowly rotating in the cold emptiness between the stars. This nebula, composed primarily of hydrogen and helium left over from the Big Bang, along with heavier elements forged in the nuclear furnaces of ancient stars, began to collapse under its own gravity. As it contracted, it spun faster, flattening into a disk with a dense, hot center that would eventually ignite to become our sun. Within this swirling disk of cosmic material, countless tiny grains of dust began to stick together through electrostatic forces and gentle collisions. These microscopic building blocks, no larger than the particles in cigarette smoke, slowly aggregated into pebbles, then boulders, then mountainous chunks of rock and metal. This process, known as accretion, was not rapid by human standards. It unfolded over millions upon millions of years, each collision adding mass and gravitational pull to the growing bodies. As these planetesimals, as astronomers call them, continued to collide and merge, they began to generate tremendous amounts of heat. Every impact, no matter how small, converted the kinetic energy of motion into thermal energy. When two house-sized chunks of rock collided at speeds of several kilometers per second, the energy released was equivalent to massive explosions. But unlike explosions that dissipate their energy into the surrounding space, these impacts occurred on bodies that were rapidly growing in mass, trapping that thermal energy within their expanding bulk. The early Earth was not born as a single cataclysmic event, but rather assembled grain by grain, boulder by boulder, planetesimal by planetesimal over perhaps 50 to 100 million years. With each collision, our planet grew not only in size but in temperature. The gravitational energy of infall was immense. As objects struck the growing Earth, they were accelerated by gravity to tremendous velocities, sometimes exceeding 10 kilometers per second by the time they impacted the surface. The energy released by such collisions was sufficient to vaporize both the incoming projectile and portions of the surface it struck. But impact heating was not the only source of thermal energy warming the young Earth. Deep within the rocky material that was accreting to form our planet, radioactive elements were undergoing decay at rates far higher than anything we observe today. Isotopes, such as aluminum-26, with a half-life of only 700,000 years, were present in much higher concentrations during the early solar system than they are now. As these unstable atoms decayed, they released energy in the form of heat, warming the interior of the growing planet from within. The combination of impact heating and radioactive decay created conditions unlike anything in Earth's subsequent history. As more and more material accumulated, the growing planet's gravity became stronger, compressing the interior and generating additional heat through the simple act of gravitational compression. The deeper layers experienced pressures and temperatures that rose inexorably as the mass above them increased. At depths of just a few hundred kilometers, temperatures climbed beyond the melting point of rock, creating pockets and eventually vast regions of molten material. This heating process was not uniform throughout the growing planet. The outer layers, exposed to the cold of space, could radiate heat away and remain relatively cool, at least temporarily. But beneath this thin, solid shell, temperatures continued to climb. The interior began to melt, creating a complex system where solid material floated on or sank through layers of molten rock and metal, depending on their density and composition. As Earth approached its current size, the energy input from impacts and radioactive decay had heated the planet to such an extent that much of its interior existed in a molten state. The surface, constantly bombarded by new incoming material, was repeatedly melted and remelted. Any solid crust that managed to form during brief lulls in the bombardment was quickly destroyed by the next wave of impacts. The boundary between the solid surface and molten interior became increasingly blurred, with the solid zone shrinking and the molten zone expanding until, eventually, the entire outer portion of the planet existed as a sea of liquid rock. The formation of this global magma ocean was not a single dramatic event, but rather the culmination of millions of years of gradual heating and melting. As the molten zone expanded upward from the deep interior, it eventually breached the surface, creating vast lakes and seas of liquid rock. These molten pools grew and merged until they covered the entire planet in an unbroken ocean of magma that extended from the surface down to depths of hundreds, perhaps thousands of kilometers. The magma ocean was not a static body of molten rock, but rather a dynamic, churning system driven by powerful convection currents. Heat from the interior rose through the liquid rock, carrying with it dissolved minerals and gases. At the surface, this hot material spread outward, cooled slightly through radiation to space, and then sank back down to complete the convection cycle. The entire ocean was in constant motion, with currents and eddies that redistributed heat and chemical components throughout the molten mass. Within this sea of liquid fire, a process of fundamental importance to Earth's future was taking place. The intense heat had melted not just the rocky material of the planet's outer layers, but had also mobilized the heavier metallic components, primarily iron and nickel, that were scattered throughout the early Earth's composition. These dense metals, now liquefied, began to respond to gravity in a way that would reshape the planet's internal structure forever. The process of planetary differentiation had begun. In the churning currents of the magma ocean, droplets and streams of molten metal, being much denser than the surrounding molten rock, began to sink toward the planet's center. This was not a rapid process by human standards, but over geological time, it was remarkably efficient. The liquid iron and nickel percolated downward through the molten rock matrix, following pathways of least resistance and gradually accumulating in the deep interior. As these metallic melts descended, they carried with them not only iron and nickel, but also other elements that had chemical affinities for metals. Gold, platinum, and other precious metals that today are rare at Earth's surface were swept downward during this great differentiation event, becoming concentrated in the planet's core, where they remain to this day. Conversely, lighter elements such as silicon, aluminum, and magnesium, which formed chemical bonds with oxygen to create various silicate minerals, remained in the molten rock layers above. The segregation of metal from silicate rock during the magma ocean phase established Earth's basic internal structure. The dense core of iron and nickel that formed during this time eventually cooled and partially solidified, creating the metallic heart of our planet that generates the magnetic field protecting us from harmful solar radiation. Above this core, the remaining silicate material formed what we now call the mantle, a thick shell of rock that, while solid today at most depths, can still flow slowly over geological timescales. This differentiation process was aided by the extreme conditions within the magma ocean. The high temperatures ensured that both silicate and metallic materials remained fluid enough to move and separate according to their densities. The convective motion within the ocean helped to bring metallic particles into contact with each other, allowing them to coalesce into larger drops that could sink more efficiently. The great depth of the magma ocean provided ample time and distance for this separation to occur, ensuring that the differentiation was thorough and complete. The chemical composition of the magma ocean itself was far from uniform. As different types of incoming material continued to bombard the surface, they added their own distinctive chemical signatures to the molten mass. Asteroids rich in water-bearing minerals contributed hydrogen and oxygen. Comets from the outer solar system brought not only water, but also carbon dioxide, methane, and ammonia. Rocky planetesimals added silicon, magnesium, iron, and dozens of other elements to the mix. Each addition to the magma ocean created new possibilities for chemical reactions and mineral formation. As temperatures fluctuated with depth and time, different minerals would crystallize out of the melt, only to be redissolved as conditions changed. This constant dissolution and reprecipitation created a complex chemical environment where elements could be redistributed and concentrated in ways that would prove crucial for Earth's later evolution. The depth of the magma ocean during its peak extent remains a subject of scientific investigation, but evidence suggests it may have extended down to depths of 1,000 kilometers or more. This would mean that the molten zone encompassed not just the surface and shallow interior, but penetrated deep into what would eventually become the solid mantle. The pressure at such depths was enormous, equivalent to hundreds of thousands of times the atmospheric pressure at Earth's surface today, and these extreme conditions allowed for the formation of mineral phases that cannot exist under normal surface conditions. At the surface of the magma ocean, conditions were equally extreme but in different ways. The temperature of the molten rock at the surface likely exceeded 2,000 degrees Celsius, hot enough to melt copper or even iron. The surface glowed with the intense heat of the underlying molten rock, radiating energy into space in the form of visible light and infrared radiation. From space, the early Earth would have appeared as a glowing ember, orange-red with heat and utterly unlike the blue marble we see today. Above this molten surface, the atmosphere was unlike anything that has existed on Earth since. The intense heat drove massive amounts of vaporization, sending clouds of rock vapor and metallic gases high into the atmosphere. Silicon, magnesium, iron, and other elements that normally exist only in solid form were present as gases in the early atmosphere, creating a dense, opaque envelope that trapped heat and prevented efficient cooling of the surface. The atmospheric pressure during the magma ocean phase was likely many times greater than today's atmospheric pressure. This thick atmosphere was composed not of the nitrogen and oxygen that we breathe, but rather of water vapor, carbon dioxide, hydrogen, and various other gases that had been outgassed from the molten rock below. The high pressure allowed water to remain liquid at temperatures that would normally cause it to boil away into steam, though whether any liquid water could actually exist on the surface during the peak of the magma ocean phase remains uncertain. The boundary between the molten surface and the dense atmosphere above was not sharp and well defined as the boundary between land and air is today. Instead, there was a gradual transition from the liquid rock below through increasingly gas-rich layers to the purely gaseous atmosphere above. Rock vapor condensed and rained back down onto the surface, while new material was constantly being vaporized by the intense heat, creating a dynamic exchange between the solid, liquid, and gaseous phases of matter. This early atmosphere was also the repository for many of the volatile elements and compounds that would later prove essential for life. Water, carbon dioxide, nitrogen compounds, and organic molecules were all present in the dense atmospheric envelope surrounding the molten planet. While these materials could not condense into liquid form at the surface during the hottest phases of the magma ocean period, they were preserved in the atmosphere, waiting for the eventual cooling that would allow them to condense and begin the long process of creating Earth's oceans and the chemical environment necessary for life. The energy balance of the magma ocean Earth was dominated by the ongoing accretion of new material from space. Each impact not only added mass to the planet, but also contributed enormous amounts of kinetic energy that was converted to heat upon collision. The largest impacts could vaporize thousands of cubic kilometers of rock, sending shockwaves deep into the planet's interior and maintaining the molten state of the surface layers. However, this process of accretion was not destined to continue indefinitely in the same gradual manner. As Earth approached approximately 90% of its current mass, an event occurred that would fundamentally alter the trajectory of our planet's evolution and create the most extensive magma ocean in its history. This was the collision with Theia, a Mars-sized planetary body that had been forming in a similar orbit around the young Sun. Theia had likely originated from the same population of planetesimals that gave birth to Earth, but had followed a slightly different evolutionary path. Computer simulations suggest that this protoplanet may have formed at one of the gravitationally stable points in Earth's orbital path, known as Lagrange points, where the combined gravitational forces of Earth and the Sun created a stable zone for planetary formation. For millions of years, Theia and Earth coexisted in this delicate gravitational dance, each growing larger through continued accretion while maintaining their orbital relationship. The eventual collision between Earth and Theia was not the result of a sudden catastrophic change in their orbits, but rather the inevitable outcome of gravitational perturbations that slowly destabilized their arrangement over geological time. As both bodies continued to grow in mass, their gravitational influence on each other increased, eventually reaching a point where their orbital relationship became unstable. Small perturbations, perhaps caused by gravitational influences from Jupiter or other growing planets, gradually nudged Theia out of its stable configuration. When the collision finally occurred, approximately 4.5 billion years ago, it represented the most energetic event in Earth's history. The impact velocity was estimated at several kilometers per second, and the kinetic energy released was equivalent to billions of the most powerful nuclear weapons ever created by humanity, all detonated simultaneously. The collision was not a head-on impact, but rather an oblique strike, with Theia approaching Earth at an angle that would prove crucial for the eventual formation of our moon. The immediate effects of this collision were almost beyond comprehension. The impact site was instantaneously vaporized, with temperatures reaching tens of thousands of degrees, hot enough to break apart atoms themselves and create a plasma of free electrons and atomic nuclei. Shockwaves propagated through both bodies at velocities exceeding the speed of sound in rock, carrying enormous amounts of energy deep into their interiors. The crust and much of the mantle of both Earth and Theia were completely melted within hours of the impact. A significant portion of both planetary bodies was ejected into space during the collision, forming a disk of debris around the newly merged planet. This ejected material included vaporized rock, molten droplets, and solid fragments ranging in size from dust particles to mountain-sized chunks. The debris disk extended from just above Earth's surface out to several times the distance of the current moon's orbit, creating a temporary ring system around our planet that glowed with the heat of molten and vaporized rock. The collision thoroughly mixed the materials of both Earth and Theia, creating a hybrid composition that would characterize our planet from that point forward. Chemical analysis of moon rocks brought back by Apollo missions has revealed isotopic signatures that confirm this mixing, showing that the moon formed from the combined material of both bodies rather than from Earth alone. The impact also transferred significant angular momentum to Earth, spinning the newly enlarged planet much faster than before and tilting its rotational axis to create the seasonal variations we experience today. The energy released by the giant impact was sufficient to melt the entire outer portion of the enlarged Earth to depths of potentially 2,000 kilometers or more. This created the most extensive magma ocean in our planet's history, far deeper and more long-lasting than any that had existed during the earlier phases of accretion. The surface of post-impact Earth was completely molten, with no solid crust anywhere on the planet's surface. The thermal energy from the collision was so immense that it took millions of years for the planet to cool sufficiently for any solid material to form at the surface. During this time, Earth existed as a ball of molten rock surrounded by a dense atmosphere of rock vapor and other gases. The surface temperature exceeded 3,000 degrees Celsius, well above the melting point of any known rock type. The entire planet glowed with incandescent heat, radiating energy into space at a rate that gradually but steadily reduced the internal temperature. Within this post-impact magma ocean, the process of planetary differentiation resumed on an even grander scale than before. The collision had thoroughly remixed the interior of the planet, undoing much of the earlier separation between metallic and silicate materials. Once again, droplets of molten iron and nickel began their journey toward the planet's center. But now they had to traverse an even deeper ocean of molten rock. The differentiation process following the giant impact was more efficient than the earlier phases because the entire system was molten and could flow freely. There were no solid barriers to impede the movement of dense metallic liquids toward the center or light silicate liquids toward the surface. This thorough redifferentiation established the modern structure of Earth's interior, with a large iron-nickel core surrounded by a silicate mantle. As the core formed during this phase, it released additional gravitational energy as the dense metallic material settled into the planet's center. This energy helped to maintain the molten state of the outer layers, prolonging the existence of the magma ocean for millions of years beyond what would have been possible from the impact energy alone. The formation of the core was a gradual process, with metallic material continuously raining down through the molten silicate matrix over periods measured in millions of years. The chemical consequences of the giant impact and subsequent core formation were profound. Elements that have strong chemical affinities for iron, known as siderophile elements, were preferentially incorporated into the descending metallic phase and became concentrated in the core. This includes not only iron and nickel, but also precious metals such as gold, platinum, and palladium. The depletion of these elements from Earth's mantle, relative to their abundance in meteorites, provides strong evidence for the core formation process that occurred during the magma ocean phase. Conversely, elements that prefer to remain in silicate minerals, known as lithophile elements, were concentrated in the mantle. These include silicon, aluminum, magnesium, and many other elements that would later become important components of crustal rocks. The partitioning of elements between core and mantle during the magma ocean phase established the fundamental chemical architecture of our planet that persists to this day. The atmosphere above the post-impact magma ocean was unlike anything that had existed before or would exist again in Earth's history. The enormous energy of the collision had vaporized vast quantities of rock, creating an atmosphere rich in silicon, magnesium, iron, and aluminum vapors. These normally solid elements existed as gases in the dense, hot atmosphere, along with more traditional atmospheric components such as water vapor, carbon dioxide, and hydrogen. The atmospheric pressure during this phase may have exceeded 100 times the current atmospheric pressure, creating conditions where the boundary between the molten surface and the gaseous atmosphere became increasingly blurred. Rock vapor condensed and rained back down onto the surface in a bizarre form of precipitation, unlike anything in the modern world. Meanwhile, Continued vaporization from the molten surface fed new material into the dense atmospheric envelope. This thick atmosphere acted as an efficient thermal blanket, trapping heat radiated from the molten surface and slowing the cooling process. The greenhouse effect created by the dense atmosphere of rock vapor and traditional greenhouse gases maintained surface temperatures well above the melting point of rock for extended periods. Only as the atmosphere gradually cooled and allowed some of the rock vapor to condense did the rate of heat loss to space begin to exceed the rate of heat generation from the planet's interior. The cooling of the magma ocean was not a uniform process but occurred in stages, with different regions and different depths cooling at different rates. The surface, exposed to the cold of space, was the first region to begin cooling, despite the insulating effect of the thick atmosphere. As the surface temperature dropped below the vaporization point of rock, the rate of material being added to the atmosphere decreased, allowing the atmospheric pressure to gradually decline. The first solid materials to form at the surface were those with the highest melting points. Minerals rich in magnesium and iron, such as olivine and pyroxene, were among the earliest to crystallize from the cooling magma ocean. These dense minerals, being heavier than the remaining liquid, sank back into the molten interior, creating a continuous cycle of crystallization and recycling that helped to further differentiate the chemical composition of different layers within the magma ocean. As cooling progressed, minerals with progressively lower melting points began to crystallize. Feldspar minerals, rich in aluminum and silicon, formed at somewhat lower temperatures and, being less dense than the mafic minerals that crystallized earlier, tended to accumulate near the surface. This process of fractional crystallization created the first chemical differentiation between what would eventually become the oceanic crust, rich in dense mafic minerals, and the continental crust, enriched in lighter, more silica-rich components. The formation of the first stable solid crust was a gradual process that occurred over millions of years. Initially, thin skins of solid rock would form at the surface during periods of relatively rapid cooling, only to be broken up and remelted by convective currents in the underlying magma ocean. These early crustal fragments were unstable and short-lived, constantly being recycled back into the molten interior. Eventually, as the overall temperature of the magma ocean continued to decline, these crustal fragments became larger and more persistent. The thickness of the solid layer increased, providing greater insulation for the molten interior and further slowing the cooling process. The formation of stable crust marked a critical transition in Earth's evolution, creating the first permanent solid surface that could serve as a foundation for the geological processes that would follow. The composition of this earliest crust was quite different from any rock type commonly found at Earth's surface today. The extreme conditions under which it formed, including the high temperatures, pressures, and unique chemical environment of the magma ocean, created mineral assemblages that are now rare or extinct. Some scientists theorize that this primordial crust may have been composed largely of komatiite, an ultramafic rock type that requires extremely high temperatures to form and is now found only in very ancient geological formations. Even as solid crust began to form and persist at the surface, the interior of the planet remained largely molten. The magma ocean did not solidify uniformly from top to bottom, but rather developed a complex structure with solid regions interspersed with molten zones at various depths. The deep interior, insulated by the overlying rock and continuously heated by radioactive decay and gravitational compression, remained molten long after the surface had solidified. The transition from a fully molten surface to one with permanent solid crust created new possibilities for geological processes. Volcanic activity became possible as molten rock from the interior could now erupt through fractures in the solid crust. These early volcanoes were likely far more extensive and violent than any volcanic activity in recorded history, as they were fed by the vast reservoirs of molten rock that still existed in the shallow interior. The solidification of the magma ocean also marked the beginning of the hydrological cycle on Earth. As the surface temperature dropped below the boiling point of water, water vapor in the atmosphere could finally condense into liquid form. The first rains in Earth's history began to fall, creating temporary pools and lakes on the newly formed solid surface. However, the surface was still extremely hot, and much of this early rainfall immediately vaporized upon contact with the hot rock, creating a dynamic cycle of evaporation and condensation. The early atmosphere during the late stages of magma ocean cooling was still radically different from today's atmosphere. It contained virtually no free oxygen, as oxygen-producing life forms had not yet evolved. Instead, the atmosphere was rich in reducing gases such as hydrogen, methane, and ammonia, along with large quantities of water vapor and carbon dioxide outgassed from the cooling magma ocean. This reducing atmosphere would have been toxic to most modern life forms, but may have provided the chemical conditions necessary for the first steps in the origin of life. The outgassing process that created this early atmosphere was driven by the continuous cooling and crystallization of the magma ocean. As molten rock cooled and solidified, dissolved gases were released, much like the way carbon dioxide is released when a carbonated beverage is opened. The scale of this outgassing was enormous, involving the release of gases from thousands of cubic kilometers of molten rock over millions of years. Different types of gases were released at different stages of the cooling process, depending on their solubility in molten rock and the temperature and pressure conditions at various depths. Water vapor was among the most abundant gases released, eventually providing the source material for Earth's oceans. Carbon dioxide was also released in large quantities, creating a significant greenhouse effect that helped to regulate the cooling rate of the surface. The magnetic field of Earth, generated by convective motion in the liquid iron core, may have begun to develop during the late stages of magma ocean solidification. As the core differentiated and developed a solid inner region surrounded by a liquid outer region, the conditions necessary for generating a magnetic field through the dynamo effect were established. This early magnetic field would have provided crucial protection for the developing atmosphere and any early life forms from the harmful effects of solar radiation and cosmic rays. The late heavy bombardment, a period of intense asteroid and comet impacts that occurred between 4 and 3.8 billion years ago, represented the final major disruption to the cooling magma ocean. During this period, the inner solar system experienced a renewed phase of heavy bombardment as gravitational perturbations from the giant planets destabilized populations of asteroids and comets, sending them on collision courses with the terrestrial planets. The impacts during the late heavy bombardment were capable of remelting portions of Earth's newly formed crust, creating localized magma oceans that persisted for thousands of years before cooling again. The largest of these impacts may have been powerful enough to disrupt the entire crustal formation process, essentially restarting the magma ocean phase in certain regions of the planet. However, by this time, Earth had cooled sufficiently that these impact-generated magma oceans were temporary and localized, rather than global and long-lasting. Each major impact during this period added new material to Earth's surface, including water-rich comets and asteroids, that contributed to the growing inventory of volatile compounds in the atmosphere and on the surface. These impacts also created complex crater structures that would later be filled with water to form some of Earth's earliest large bodies of liquid water. The energy released by these impacts temporarily raised atmospheric temperatures and may have periodically sterilized the surface, but they also contributed essential materials for the eventual development of life. The chemical evolution of Earth's surface during the final stages of magma ocean cooling was influenced by the continuing influx of extraterrestrial material. Different types of asteroids and comets brought distinct chemical signatures, adding to the growing complexity of Earth's surface composition. Carbonaceous asteroids contributed organic compounds and water, while metallic asteroids added iron, nickel, and platinum group elements to the surface inventory. The gradual establishment of a stable, solid crust marked the end of the magma ocean phase and the beginning of Earth's transition toward the planet we recognize today. However, This transition was not abrupt, but rather extended over hundreds of millions of years. Even after the surface had solidified, the interior remained hot and partially molten, driving continued volcanic activity and geological processes that would shape the planet's surface for billions of years to come. The legacy of the magma ocean phase is preserved in the fundamental structure of our planet. The differentiation between core and mantle that occurred during this period established the basic architecture of Earth's interior. The chemical signatures created by the extreme conditions of the magma ocean can still be detected in ancient rocks and provide crucial evidence for understanding this earliest chapter in our planet's history. Modern scientific investigation of the magma ocean phase relies on multiple lines of evidence, including computer modeling of planetary formation processes, experimental studies of rock behavior at extreme temperatures and pressures, and analysis of the oldest surviving rocks and minerals on Earth's surface. Zircon crystals from the Jack Hills of Western Australia, dating to over 4 billion years ago, provide direct evidence of the conditions that existed during the late stages of magma ocean cooling. These ancient zircons contain chemical signatures that indicate they formed in the presence of liquid water, suggesting that the transition from magma ocean to solid surface occurred more rapidly than previously thought. The preservation of these crystals through billions of years of geological activity provides a remarkable window into the earliest history of our planet and demonstrates that solid crust and liquid water may have coexisted on Earth's surface earlier than once believed possible. The isotopic composition of these ancient minerals also provides insights into the temperature and chemical conditions under which they formed. Oxygen isotope ratios in ancient zircons suggest that the early Earth had developed a hydrological cycle by 4 billion years ago, with liquid water present at the surface and actively participating in rock formation processes. This evidence indicates that the harsh conditions of the magma ocean phase gave way relatively quickly to more moderate surface conditions suitable for the preservation of liquid water. The study of other planetary bodies in our solar system has provided additional perspective on the magma ocean phase of Earth's history. The Moon, which formed as a direct result of the giant impact that created Earth's most extensive magma ocean, preserves evidence of its own magma ocean phase in the form of ancient crustal rocks. Analysis of lunar samples has revealed details about the crystallization sequence and chemical evolution of magma oceans that complement our understanding of Earth's early history. Mars, Venus, and even some of the largest asteroids show evidence of having experienced magma ocean phases during their early history. These comparative studies suggest that magma oceans were a common feature of planetary formation in the inner solar system and provide insights into the range of conditions and outcomes possible during this crucial phase of planetary evolution. The fact that Earth's magma ocean phase led to the development of a habitable planet, while similar processes on other worlds did not highlight the complex interplay of factors that determined our planet's unique evolutionary path. The duration of Earth's magma ocean phase remains a subject of ongoing scientific investigation, with estimates ranging from several million to several hundred million years, depending on the specific conditions assumed in different models. The cooling rate was controlled by a delicate balance between heat generation from radioactive decay and gravitational compression on one hand, and heat loss through radiation to space on the other. Small changes in atmospheric composition, impact frequency, or internal heat generation could significantly affect this balance and alter the duration of the molten phase. Recent advances in high-pressure experimental techniques have allowed scientists to recreate some of the extreme conditions that existed within Earth's magma ocean, providing new insights into the behavior of molten rock under the pressures and temperatures that characterize the planet's deep interior. These experiments have revealed unexpected properties of molten silicate materials at extreme conditions, including changes in density and chemical behavior that affect models of how the magma ocean evolved and solidified. The transition from magma ocean to solid planet represents one of the most fundamental transformations in Earth's history, comparable in significance to the origin of life or the development of plate tectonics. This transition established the basic physical and chemical framework within which all subsequent geological and biological evolution would occur. The differentiated structure of the planet, the composition of the atmosphere and oceans, and even the magnetic field that protects us from harmful radiation, all trace their origins to processes that occurred during the magma ocean phase. Understanding this early period of Earth's history also provides crucial insights for the search for life on other planets. The magma ocean phase appears to be a common feature of terrestrial planet formation, suggesting that other worlds may have undergone similar processes. The conditions under which Earth's magma ocean evolved to create a habitable planet provide important constraints for identifying potentially habitable worlds around other stars and understanding the factors that determine planetary habitability. The story of Earth's magma ocean is ultimately a story of transformation and possibility. From the violent chaos of planetary formation emerged the stable, differentiated world that would eventually nurture the development of life. The extreme conditions that characterize this earliest phase of our planet's history were not obstacles to overcome, but rather necessary steps in the process that created the world we inhabit today. Every feature of our planet, from the continents beneath our feet to the magnetic field that protects us from space, carries within it the legacy of that ancient ocean of fire that once covered our entire world. As the magma ocean began its long journey towards solidification, the processes occurring within its depths were setting the stage for one of the most remarkable chapters in planetary science. The crystallization of this global sea of molten rock was not a simple cooling process, but rather a complex dance of physics and chemistry that would determine the fundamental character of our planet for billions of years to come. The first minerals to crystallize from the cooling magma ocean were those with the highest melting points, primarily olivine and pyroxene, minerals rich in magnesium and iron. These early crystals formed at temperatures exceeding 1500 degrees Celsius, emerging like islands of solid matter in an ocean of liquid fire. But their fate was not to remain at the surface. Being denser than the surrounding molten rock, these crystalline grains began to sink, descending through the convecting magma like metallic rain falling through a luminous atmosphere. This process of fractional crystallization fundamentally altered the composition of the magma ocean as it cooled. As the dense iron-rich minerals settled toward the bottom, the remaining liquid became progressively enriched in lighter elements such as aluminum, silicon, and alkali metals. This chemical evolution occurred simultaneously with the physical cooling, creating layers of different composition at different depths within the crystallizing ocean. The convection currents that dominated the early magma ocean played a crucial role in this differentiation process. Hot, less dense material rose from the deep interior, carrying with it dissolved chemicals and partially formed crystals. At the surface, this material cooled and became denser, then sank back down, completing vast circulation patterns that extended from the surface to depths of hundreds of kilometers. These currents ensured thorough mixing of the magma ocean's contents, while simultaneously enabling the separation of different chemical components according to their physical properties. As the cooling progressed over millions of years, the character of the crystallization process began to change. The initial phase, dominated by the formation and settling of dense minerals, gave way to a more complex period where multiple mineral phases crystallized simultaneously at different depths. The pressure increase with depth meant that the same chemical composition could form different mineral structures depending on how far below the surface crystallization occurred. At the greatest depths within the magma ocean, where pressures exceeded those found anywhere on Earth's surface today, unique high-pressure mineral phases began to form. These included varieties of pyroxene and garnet that could only exist under the extreme conditions of the deep magma ocean. Some of these mineral phases were so specific to high-pressure environments that they provide modern geologists with crucial evidence for the existence and depth of the ancient magma ocean. The formation of these deep, high-pressure minerals had profound implications for the chemical evolution of Earth's interior. Elements that might normally form separate mineral phases under surface conditions were forced to coexist within the crystal structures of high-pressure minerals, creating chemical reservoirs that would influence the composition of volcanic rocks for billions of years to come. The garnet that formed in the deep magma ocean, for example, incorporated significant amounts of aluminum and calcium, elements that would later be important components of continental crust. Meanwhile, at intermediate depths within the magma ocean, plagioclase feldspar began to crystallize as temperatures dropped below approximately 1200 degrees Celsius. This aluminum-rich mineral was less dense than the mafic minerals that had crystallized earlier, causing it to accumulate in the upper portions of the magma ocean, rather than sinking to the bottom. The formation and accumulation of plagioclase marked the beginning of the process that would eventually lead to the formation of the first stable crustal rocks. The behavior of plagioclase crystallization was particularly important because this mineral incorporates significant amounts of aluminum, an element that would become crucial for the formation of continental crust. As plagioclase crystals accumulated in the upper reaches of the magma ocean, they created the first chemical differentiation between what would eventually become oceanic crust, dominated by dense mafic minerals, and continental crust, enriched in lighter, aluminum-rich minerals. The cooling of the magma ocean was not a uniform process across the planet's surface. Regional variations in heat flow, influenced by the distribution of radioactive elements and the efficiency of convective heat transport, created areas where solidification proceeded at different rates. Some regions developed thicker accumulations of early crystalline material, while others remained molten for extended periods. These variations in the timing and character of solidification would later influence the locations where the first stable crustal blocks would form. The role of water during the magma ocean phase was complex and remains an active area of scientific research. While the extreme surface temperatures prevented liquid water from existing at the surface during the peak of the magma ocean period, water was present in other forms throughout the system. Water dissolved in the molten rock at depth, water vapor in the dense atmosphere above, and possibly even supercritical water at the interface between the molten surface and the overlying atmosphere. The solubility of water in molten silicate rock increases with pressure, meaning that the deeper portions of the magma ocean could hold substantial amounts of dissolved water. As crystallization progressed and the remaining liquid became enriched in water and other volatile components, this created conditions that would later prove crucial for the formation of the first stable crust. Water acts as a flux in silicate melts, lowering their melting temperature and changing their crystallization behavior in ways that favor the formation of more silica-rich, less dense rocks. The outgassing of water and other volatile compounds from the crystallizing magma ocean was a continuous process that lasted for millions of years. Each episode of crystallization released dissolved gases into the overlying atmosphere, gradually building up the inventory of volatile compounds that would later form Earth's oceans and contribute to its early atmosphere. This outgassing was not uniform across the surface, but occurred preferentially in regions where convective upwelling brought volatile-rich material from depth to the surface. Carbon dioxide was another important component of the outgassing process. The magma ocean contained substantial amounts of dissolved carbon dioxide, which was released as the molten rock cooled and crystallized. This carbon dioxide contributed to the dense early atmosphere and created a significant greenhouse effect that helped regulate the cooling rate of the surface. The balance between carbon dioxide outgassing and its removal from the atmosphere through reaction with newly formed crustal rocks would later become an important factor in determining Earth's surface temperature. The formation of the first stable crustal rocks was a gradual process that occurred over tens of millions of years. Initially, thin films of solid rock would form at the surface during periods of relatively rapid cooling, only to be disrupted and remelted by the continuing convective motion in the underlying magma ocean. These early attempts at crustal formation were unstable and short-lived, constantly being recycled back into the molten interior. The breakthrough came when the overall temperature of the magma ocean dropped sufficiently that the rate of heat loss to space exceeded the rate of heat generation from the interior. This critical transition allowed progressively thicker layers of solid rock to form and persist at the surface. The first stable crustal fragments were probably no more than a few kilometers thick, but they represented a fundamental change in the character of Earth's surface. These early crustal rocks were quite different in composition from any common rock type found on Earth today. The extreme conditions under which they formed, including the very high temperatures and the unique chemical environment of the late-stage magma ocean, created mineral assemblages that are now rare or extinct. The closest modern analogues are the komatiite lavas, found in some of the world's oldest geological formations. Ultra-high temperature volcanic rocks that require temperatures exceeding 1600 degrees Celsius to form. The texture and structure of these primordial crustal rocks would have been unlike anything seen in modern volcanic processes. The extremely high temperatures at which they crystallized allowed the formation of very large crystals, creating coarse-grained rocks with distinctive textures that reflected the slow cooling rates characteristic of the deep magma ocean environment. Some of these early rocks may have contained crystals several centimeters or even meters in size, formed during the prolonged crystallization process in the cooling magma ocean. As the first stable crust began to form and thicken, it created new possibilities for geological processes. The solid crust acted as an insulating layer, slowing the rate of heat loss from the interior and allowing the development of temperature gradients that would drive future volcanic activity. Fractures and weaknesses in the early crust provided pathways for molten rock from the still liquid interior to reach the surface, creating the first volcanic eruptions in Earth's history. These early volcanic eruptions were unlike any volcanic activity witnessed in recorded history. Fed by the vast reservoir of molten rock that still existed in the shallow interior, they were likely far more extensive and long-lasting than even the largest modern volcanic events. Some of these eruptions may have continued for thousands of years, building massive volcanic edifices that helped to thicken the growing crustal layer. The composition of the early volcanic rocks evolved as the magma ocean continued to crystallize and differentiate. The earliest eruptions would have been dominated by the high-temperature, magnesium-rich compositions characteristic of the deep magma ocean. As crystallization progressed and the remaining liquid became more evolved, later volcanic eruptions would have produced increasingly silica-rich compositions, contributing to the growing chemical diversity of the crustal rocks. The formation of stable crust also marked the beginning of the first sedimentary processes on Earth. Weathering of the newly formed volcanic rocks by the hot, dense atmosphere began to produce the first sedimentary particles. These early weathering processes were quite different from modern weathering, occurring at much higher temperatures and in the presence of a chemically reducing atmosphere. But they represented the first steps toward the development of sedimentary geology. The early sedimentary processes were dominated by physical rather than chemical weathering. The extreme temperature variations between day and night, caused by the planet's rapid rotation and the lack of substantial atmospheric thermal buffering, created thermal stress that helped to fracture and break down the early crustal rocks. Wind erosion in the dense early atmosphere was also more effective than it would be under modern conditions, helping to transport sedimentary particles across the surface. The accumulation of these early sedimentary deposits in low-lying areas created the first stratified rock sequences on Earth's surface. These primitive sedimentary rocks were composed primarily of fragments of the early volcanic and plutonic rocks, but they also began to incorporate chemical precipitates formed by the interaction of the hot atmosphere with the cooling crustal rocks. The formation of these early sedimentary sequences marked the beginning of the geological record, though virtually none of these ancient rocks have survived to the present day. The continued cooling of the planet's interior meant that the zone of partial melting gradually retreated to greater depths beneath the surface. The thickness of the solid crust increased steadily over time, and the character of volcanic activity began to change as magma had to travel greater distances from its source to reach the surface. This evolution in volcanic processes contributed to the growing stability and thickness of the early crustal layer. The development of stable crust also created the first opportunities for the accumulation of surface water. As the surface temperature dropped below the boiling point of water, water vapor in the atmosphere could begin to condense into liquid form. The first rainfall in Earth's history created temporary pools and lakes in low-lying areas between volcanic edifices and impact craters. However, much of this early surface water was unstable, repeatedly evaporating and condensing as surface temperatures fluctuated. The chemical composition of this early surface water was quite different from modern rainwater or seawater. It was likely acidic due to the dissolution of volcanic gases such as sulfur dioxide and hydrogen chloride, and it contained high concentrations of dissolved metals and other elements leached from the hot volcanic rocks. Despite these harsh chemical conditions, the presence of liquid water on the surface represented a crucial step toward the development of the hydrological cycle that would later become so important for life on Earth. The interaction between the early surface water and the hot crustal rocks created the first hydrothermal systems on Earth's surface. These systems, analogous to modern hot springs and geysers, but operating at much higher temperatures and with more extreme chemical compositions, played important roles in the continued chemical evolution of both the surface water and the crustal rocks. The circulation of hot water through fractured crustal rocks helped to extract and concentrate certain chemical elements, creating the first ore deposits and contributing to the growing chemical complexity of the surface environment. The formation of these early hydrothermal systems also had important implications for the origin of life. Modern research has suggested that hydrothermal environments may provide favorable conditions for the formation and concentration of organic compounds, and some scientists have proposed that life on Earth may have originated in such environments. While the extreme conditions of the Hadean hydrothermal systems would have been challenging for any form of life, they may have provided the chemical energy and concentration mechanisms necessary for the first steps in the origin of life. The magnetic field of Earth likely began to develop during the late stages of magma-ocean solidification as the differentiation of the core reached completion. The formation of a solid inner core surrounded by a liquid outer core created the conditions necessary for the generation of a magnetic field through the dynamo effect. This early magnetic field would have been crucial for protecting the developing atmosphere and any early life forms from the harmful effects of solar radiation and cosmic rays. The strength and stability of this early magnetic field may have been quite different from the modern geomagnetic field. The higher temperatures in the core, the different convection patterns in the early liquid outer core, and the continuing process of core formation may have created a magnetic field that was either stronger or weaker than today's field, and possibly more variable in its intensity and orientation. Despite these differences, the presence of any magnetic field would have provided important protection for the developing surface environment. The late heavy bombardment, which occurred between approximately 4 and 3.8 billion years ago, represented the final major disruption to the cooling and solidification processes that had been establishing Earth's early crust. During this period, a renewed phase of intense asteroid and comet impacts periodically disrupted the crustal formation process and created localized zones of remelting and renewed magmatic activity. The impacts during the late heavy bombardment varied enormously in size and energy. The smallest impacts created craters a few kilometers in diameter and had only local effects on the surrounding crustal rocks. The largest impacts, however, were capable of creating craters hundreds of kilometers across and generating enough energy to melt thousands of cubic kilometers of crustal and mantle rock. These giant impacts essentially created temporary, localized magma oceans that persisted for thousands of years before cooling and solidifying. Each major impact during this period contributed new material to Earth's surface, including both rocky material from asteroids and volatile rich material from comets. The asteroidal material added to the growing inventory of crustal rocks and contributed additional radioactive elements that helped to maintain the planet's internal heat budget. The cometary material brought water, carbon dioxide, and organic compounds that would later prove essential for the development of life. The impact craters created during the late heavy bombardment became important features of the early Earth's surface. The largest craters formed deep basins that would later be filled with water to create some of Earth's earliest large lakes or seas. The central peaks and ring structures of large impact craters also created topographic highs that influenced the flow of early surface water and the development of drainage patterns. The heat generated by the largest impacts was sufficient to drive extensive hydrothermal activity in the surrounding crustal rocks. Impact-driven hydrothermal systems were probably among the most energetic and long-lived hydrothermal environments on the early Earth, persisting for thousands of years after each major impact event. These systems may have played important roles in concentrating and processing the organic compounds delivered by cometary impacts, potentially contributing to the chemical evolution that led to the origin of life. The frequency and intensity of impacts gradually declined following the late heavy bombardment, allowing the crustal formation and cooling processes to proceed with fewer major disruptions. This transition marked the end of the most violent phase of Earth's early history and the beginning of a more stable period during which the fundamental features of the planet's surface could develop and persist. The chemical evolution of Earth's early atmosphere continued throughout the late stages of magma ocean cooling and the early development of stable crust. The composition of the atmosphere was controlled by the balance between outgassing from the cooling interior, loss of gases to space, and chemical reactions with the newly formed crustal rocks. This balance changed continuously as the surface environment evolved from the extreme conditions of the peak magma ocean period to the more moderate conditions that would eventually allow the development of life. The early atmosphere contained virtually no free oxygen, as photosynthetic organisms had not yet evolved to produce this gas. Instead, the atmosphere was dominated by reducing gases such as hydrogen, methane, and ammonia, along with substantial amounts of water vapor and carbon dioxide. This reducing atmosphere was maintained by the continued outgassing of hydrogen from the cooling interior and by the lack of any significant oxygen-producing processes. The lack of free oxygen in the early atmosphere had important implications for the chemistry of the surface environment. Without oxygen to react with iron and other metals, these elements could exist in their reduced forms and remain mobile in surface water. This created opportunities for the formation of chemical compounds and mineral assemblages that cannot form under modern, oxygen-rich conditions. Some of these ancient chemical signatures are preserved in the oldest rocks on Earth and provide important clues about the composition and chemistry of the early atmosphere. The greenhouse effect created by carbon dioxide and water vapor in the early atmosphere helped to maintain surface temperatures that were warm enough to keep water liquid, despite the fact that the young sun was significantly less luminous than it is today. This early greenhouse effect was crucial for the development of the hydrological cycle and may have been essential for creating the chemical conditions necessary for the origin of life. The density of the early atmosphere was likely much greater than today's atmosphere, possibly containing 10 to 100 times as much gas as the modern atmosphere. This dense atmosphere would have created surface pressures high enough to allow liquid water to remain stable at temperatures well above the normal boiling point of water. The high atmospheric pressure also enhanced the efficiency of atmospheric heat transport, helping to moderate temperature differences between different regions of the planet's surface. As the surface continued to cool and the first permanent bodies of liquid water began to form, the chemical interaction between the atmosphere, the surface water, and the newly formed crustal rocks became increasingly important in determining the evolution of the surface environment. The dissolution of atmospheric gases in surface water created acidic solutions that were capable of chemically weathering the early crustal rocks, extracting soluble elements and contributing to the growing chemical complexity of the early oceans. The formation of the first permanent oceans was a gradual process that occurred over millions of years as surface temperatures dropped sufficiently to allow the condensation and accumulation of large bodies of liquid water. The earliest oceans were probably quite different from modern seawater in both their chemical composition and their physical properties. They were likely much hotter than modern oceans, possibly with temperatures exceeding 60 or 70 degrees Celsius, and they contained much higher concentrations of dissolved metals and other elements leached from the hot crustal rocks. The chemical composition of the early oceans was dominated by the products of rock weathering rather than by the evaporation of seawater or biological processes that control modern ocean chemistry. High concentrations of iron, magnesium, and silica gave the early oceans a chemical signature quite different from any natural water found on Earth today. The high metal content may have given the early oceans a distinctly coloured appearance, possibly appearing green or brown rather than the blue colour characteristic of modern seawater. The circulation patterns in the early oceans were driven primarily by temperature differences created by volcanic heating and by the dense atmosphere's effect on surface winds. Without continents to create barriers to oceanic circulation, the early oceans may have had quite different current patterns from modern oceans. The high temperatures and chemical composition of the early seawater would also have affected its density and viscosity, influencing the efficiency of heat transport and the development of thermal gradients within the ocean basins. The interaction between the hot early oceans and the continuing volcanic activity created extensive underwater hydrothermal systems. These submarine hydrothermal vents were probably much more numerous and active than modern hydrothermal systems, fed by the higher heat flow from the still cooling interior and the continuing process of crustal formation. The chemical exchanges that occurred at these underwater vents contributed significantly to the evolution of seawater chemistry and may have created specialized chemical environments favorable for the origin of life. The development of the first sedimentary processes in the early oceans marked the beginning of marine geology. The weathering of crustal rocks by the hot, chemically reactive early atmosphere and oceans produced sedimentary particles that were transported by rivers and ocean currents to accumulate in marine basins. These early marine sediments were quite different from modern marine sediments, containing high proportions of volcanic debris and chemical precipitates formed under the extreme conditions of the early surface environment. The precipitation of chemical sediments from the early oceans was particularly important for removing dissolved elements from seawater and creating the first sedimentary ore deposits. The high concentrations of metals in the early oceans led to the formation of iron-rich sediments when these elements precipitated under changing chemical conditions. Some of the world's oldest and largest iron ore deposits may have formed through these early ocean chemical processes. The establishment of stable oceans also created the first opportunities for the development of complex chemical cycles that would later prove essential for life. The circulation of water between the oceans, the atmosphere, and the crustal rocks created pathways for the transport and concentration of chemical elements that would later become important nutrients for living organisms. While life had not yet appeared on Earth, the chemical foundation for biological processes was being established through these early geochemical cycles. The evidence for these early stages of Earth's history is preserved in the oldest rocks and minerals that have survived to the present day. Zircon crystals from the Jack Hills of Western Australia, some of which are over 4 billion years old, provide direct evidence of the conditions that existed during the transition from magma ocean to solid crust. The chemical composition and internal structure of these ancient zircons reveal information about the temperature, pressure, and chemical environment in which they formed. The oxygen isotope ratios preserved in these ancient zircons indicate that liquid water was present on Earth's surface by at least 4 billion years ago, and possibly earlier. This evidence suggests that the transition from the extreme conditions of the magma ocean to more moderate surface conditions suitable for liquid water occurred more rapidly than was previously thought possible. The preservation of these isotopic signatures through billions of years of geological activity provides a remarkable window into Earth's earliest history. Other chemical signatures preserved in ancient rocks provide evidence for the composition of the early atmosphere and oceans. The absence of oxidized iron minerals in rocks older than about 2.5 billion years confirms that the early atmosphere contained no significant amounts of free oxygen. The presence of certain sulfur isotope signatures in ancient rocks provides evidence for atmospheric chemistry that could only have existed under oxygen-free conditions. The study of ancient impact structures also provides important information about the conditions that existed during Earth's early history. While most of the impact craters formed during the late heavy bombardment have been erased by subsequent geological processes, a few examples of very ancient impact structures have been identified and studied. These ancient craters provide information about the size and frequency of impacts during Earth's early history and help to constrain models of how these impacts affected the development of the early crust and atmosphere. Comparative studies of other planetary bodies in the solar system have provided additional insights into the processes that shaped Earth during its early history. The Moon, which formed as a direct result of the giant impact that created Earth's most extensive magma ocean, preserves a record of its own magma ocean phase that can be studied through analysis of lunar rocks. The lunar magma ocean crystallized under somewhat different conditions than Earth's magma ocean, but many of the fundamental processes were similar. The surfaces of Mars and Venus also show evidence of early magma ocean phases, though the subsequent evolution of these planets was quite different from Earth's. Mars appears to have cooled more rapidly than Earth, leading to the early cessation of volcanic activity and the loss of its atmosphere. Venus, on the other hand, may have experienced a runaway greenhouse effect that prevented the condensation of surface water and led to the extremely hot, dry conditions that characterize the planet today. These comparative studies help to place Earth's early history in the broader context of planetary evolution in the solar system. They demonstrate that magma ocean phases were a common feature of terrestrial planet formation, but they also highlight the unique combination of factors that allowed Earth to evolve into a habitable planet. The size of Earth, its distance from the Sun, and the timing and magnitude of impacts during its early history all contributed to creating the specific conditions that allowed the development of stable oceans and, eventually, life. The transition from the magma ocean phase to the development of stable crust and oceans represents one of the most fundamental changes in Earth's history. This transition established the basic framework within which all subsequent geological and biological evolution would occur. The differentiated structure of the planet, with its iron core, silicate mantle, and evolved crust, created the foundation for plate tectonics, the process that would later reshape Earth's surface and continue to influence its evolution. The chemical evolution that occurred during the magma ocean phase also established the basic inventory of elements available at Earth's surface. The partitioning of elements between the core, mantle, and crust during planetary differentiation determined which elements would be available for the formation of crustal rocks, the development of the atmosphere and oceans, and eventually for biological processes. This chemical framework has influenced every aspect of Earth's subsequent evolution. The development of Earth's magnetic field during the late stages of magma ocean cooling created the protective envelope that shields our planet from harmful solar and cosmic radiation. This magnetic protection was essential for the preservation of the atmosphere and may have been crucial for allowing the eventual development of life. Planets that lack strong magnetic fields, such as Mars, have lost much of their atmospheres to space over geological time. The establishment of the hydrological cycle during the cooling of the magma ocean created the transport mechanisms that would later prove essential for life. The circulation of water between the atmosphere, oceans, and crustal rocks established pathways for the transport of chemical nutrients and the removal of waste products that would later be utilized by living organisms. The chemical weathering processes that began during this period created the first soil-like materials and contributed to the chemical complexity of the surface environment. Modern understanding of the magma ocean phase continues to evolve as new analytical techniques and computational methods provide increasingly detailed insights into this ancient period of Earth's history. High-pressure experiments that recreate the conditions within the magma ocean have revealed unexpected properties of molten rock at extreme conditions, leading to new models of how the magma ocean evolved and solidified. Advanced computer simulations that can model the complex physics and chemistry of magma ocean processes have provided new insights into the timescales and mechanisms involved in planetary differentiation. These simulations suggest that some aspects of magma ocean evolution may have occurred more rapidly than previously thought, while others may have taken longer to complete. The discovery of exoplanets orbiting other stars has also provided new perspectives on the magma ocean phase of planetary evolution. Some of these exoplanets are thought to be currently in magma ocean phases, providing opportunities to observe these processes in action around other stars. The study of these distant worlds may help to refine our understanding of how common magma ocean phases are in planetary formation and what factors determine their evolution. The search for evidence of Earth's magma ocean period has led scientists to examine some of the most ancient materials preserved on our planet, and among the most remarkable of these are tiny crystals of zircon found in the Jack Hills region of Western Australia. These crystals, no larger than a grain of sand, represent time capsules that have survived for over 4 billion years, carrying within their crystal structure chemical signatures from the earliest phases of our planet's history. Zircon is a remarkably durable mineral, capable of surviving conditions that would destroy most other rock-forming minerals. Its crystal structure incorporates uranium atoms that decay radioactively over time, providing a natural clock that allows scientists to determine precisely when each crystal formed. The oldest of these zircons date to 4.4 billion years ago, placing their formation during the final stages of the magma ocean period, when the first solid materials were beginning to crystallize from the cooling molten surface. The chemical composition of these ancient zircons reveals crucial information about the environment in which they formed. Oxygen isotope ratios preserved within the crystal structure indicate that liquid water was present on Earth's surface much earlier than previously thought possible. The specific ratios of different oxygen isotopes can only be produced through interactions between hot rock and liquid water, suggesting that even during the late stages of the magma ocean period, conditions had moderated sufficiently to allow water to exist in liquid form at the surface. This evidence for early liquid water has profound implications for our understanding of how rapidly Earth's surface environment evolved from the extreme conditions of the peak magma ocean period to more moderate conditions suitable for the eventual development of life. The presence of liquid water indicates that surface temperatures had dropped below 100 degrees Celsius in at least some locations, representing a dramatic cooling from the thousands of degrees that characterized the early magma ocean surface. The hafnium isotope signatures preserved in these ancient zircons provide additional insights into the processes occurring during the late magma ocean period. Hafnium is chemically similar to zirconium and becomes incorporated into zircon crystals as they form. The isotopic composition of hafnium reflects the composition of the source material from which the zircons crystallized, providing information about the chemical evolution of Earth's early crust. The hafnium signatures in the oldest zircons suggest that they crystallized from magmas that had already undergone significant chemical differentiation. This indicates that the processes of fractional crystallization and chemical separation that characterized the magma ocean period had progressed far enough to create chemically distinct reservoirs of molten rock with different compositions. The formation of these chemically evolved magmas required millions of years of crystallization and differentiation within the cooling magma ocean. Trace element compositions preserved in ancient zircons provide further evidence for the conditions under which they formed. Elements such as titanium, which is incorporated into zircon crystals in temperature-dependent amounts, indicate that these crystals formed at temperatures consistent with crystallization from evolved, silica-rich magmas rather than from the high-temperature primitive compositions that characterize the early magma ocean. This chemical evidence supports the interpretation that these zircons formed during the late stages of magma ocean evolution, when extensive fractional crystallization had created more evolved melt compositions. The preservation of these ancient zircons through billions of years of geological activity is itself remarkable and provides insights into the early crustal processes that occurred during and after the magma ocean period. The fact that these crystals have survived indicates that they were incorporated into crustal rocks that were sufficiently stable to avoid complete recycling back into the mantle. This suggests that the formation of stable continental crust began very early in Earth's history, possibly during the final stages of magma ocean solidification. The geographic distribution of ancient zircons provides additional clues about the early crustal formation processes. While the oldest zircons are found primarily in a few locations such as the Jack Hills of Australia, similar though somewhat younger zircons have been found in ancient rock formations on other continents. This distribution suggests that the processes that created these early crustal materials operated on a global scale, rather than being restricted to isolated regions. Studies of younger zircons from the same formations reveal a continuous record of crustal formation and evolution extending from the Hadean Eon through the Archean Eon and into more recent geological time. The chemical evolution recorded in these zircons shows a progressive change from the extreme conditions of the late magma ocean period toward more moderate conditions, characteristic of a planet with stable crust and surface water. This evolutionary sequence provides a detailed record of how Earth's surface environment evolved during the critical transition period following the end of the magma ocean phase. The study of inclusions within ancient zircons has provided additional insights into the early Earth environment. Some zircons contain tiny inclusions of other minerals that were trapped during crystallization. These mineral inclusions preserve samples of the magmas and fluids that were present during zircon formation, providing direct evidence for the chemical and physical conditions that existed during the late magma ocean period. Quartz inclusions within some ancient zircons indicate that the magmas from which they crystallized were rich in silica, confirming that significant chemical differentiation had occurred by the time these crystals formed. The presence of quartz also provides additional evidence that temperatures had moderated sufficiently to allow the crystallization of minerals with relatively low melting points. The formation of quartz-bearing magmas requires temperatures below approximately 1,200 degrees Celsius, much lower than the temperatures that characterize the early magma ocean. Some ancient zircons also contain inclusions of muscovite, a mica mineral that contains water in its crystal structure. The preservation of muscovite inclusions provides direct evidence that water was available during the crystallization of these zircons and that it was incorporated into the early crustal rocks. The presence of hydrous minerals in these ancient materials supports other evidence for the early presence of liquid water at Earth's surface. The carbon isotope signatures preserved in some ancient zircons have been interpreted as potential evidence for very early biological activity, though this interpretation remains controversial within the scientific community. Carbon, with isotopic compositions similar to those produced by biological processes, has been found in some zircons older than 4 billion years. However, determining whether this carbon signature reflects actual biological activity or abiotic chemical processes remains an active area of research and debate. The chromium isotope compositions preserved in ancient zircons provide information about the oxidation state of the early Earth environment. Chromium isotopes are sensitive to the availability of oxygen, and the signatures preserved in ancient zircons confirm that the early Earth environment was highly reducing, with virtually no free oxygen present in the atmosphere or surface water. This evidence supports other indicators that photosynthetic organisms had not yet evolved to produce significant amounts of atmospheric oxygen. Advanced analytical techniques have allowed scientists to examine the internal structure of ancient zircons at microscopic scales, revealing details about how these crystals grew and evolved over time. Some zircons show complex internal structures with multiple growth zones that record changing chemical and physical conditions during crystallization. These growth patterns provide insights into how magma compositions evolved during the cooling and crystallization of the late magma ocean. Cathodoluminescence imaging, which reveals internal structures within zircon crystals, has shown that some ancient zircons experienced multiple episodes of recrystallization and alteration after their initial formation. These later modifications record subsequent geological events that affected the early crustal rocks, including metamorphism, weathering, and incorporation into younger rock formations. The ability to distinguish between original magmatic signatures and later modifications is crucial for interpreting what these ancient crystals reveal about early Earth conditions. Ion microprobe analysis techniques have enabled scientists to measure isotopic compositions within individual zones of single zircon crystals, providing unprecedented detail about the chemical evolution of early Earth materials. These high-precision measurements have revealed that some ancient zircons preserve multiple generations of growth, each recording slightly different environmental conditions. This detailed record provides insights into how rapidly conditions were changing during the transition from magma ocean to stable crust. The lead isotope compositions of ancient zircons provide information about the age and origin of the source materials from which they crystallized. Lead isotopes in zircon are produced by the radioactive decay of uranium over geological time, and the accumulated lead provides information about how long uranium had been present in the source materials before zircon crystallization occurred. These measurements indicate that the source materials for the oldest zircons had undergone chemical differentiation for tens of millions of years before the zircons themselves formed. Studies of ancient zircons from different geographical locations have revealed both similarities and differences in their chemical signatures, providing insights into regional variations in early crustal formation processes. While all ancient zircons share certain characteristics that reflect the global conditions of the late magma ocean period, subtle differences in their compositions suggest that local variations in temperature, pressure, and chemical environment influence their formation. The rare earth element patterns preserved in ancient zircons provide additional constraints on the magmatic processes that created them. Rare earth elements are incorporated into zircon crystals in predictable patterns that reflect the composition and evolution of the magmas from which they crystallized. The patterns observed in ancient zircons are consistent with crystallization from highly evolved silica-rich magmas that had undergone extensive fractional crystallization, supporting models for progressive chemical differentiation during magma ocean cooling. Temperature estimates derived from titanium concentrations in ancient zircons indicate crystallization temperatures between 650 and 750 degrees Celsius, much lower than the temperatures that characterize the early magma ocean, but consistent with crystallization from evolved magmas during the late stages of crustal formation. These temperature estimates provide quantitative constraints on the thermal evolution of Earth's surface environment during the critical transition period following the end of the magma ocean phase. The water content of magmas from which ancient zircons crystallized can be estimated from the trace element compositions of the zircons themselves. These estimates suggest that the late-stage magmas contained several % dissolved water, indicating that substantial amounts of water had been incorporated into the early crustal formation processes. The presence of water in these magmas would have lowered their crystallization temperatures and influenced their chemical evolution in ways that favored the formation of more silica-rich compositions. Experimental studies aimed at reproducing the conditions under which ancient zircons formed have provided additional insights into the early Earth environment. Laboratory experiments conducted at high temperatures and pressures similar to those inferred for the late magma ocean period have successfully synthesized zircons with chemical compositions similar to those of natural ancient zircons. These experiments help to validate interpretations of the natural samples and provide constraints on the physical and chemical conditions required for their formation. The study of ancient zircons has also provided insights into the early development of Earth's magnetic field. Some ancient zircons preserve magnetic signatures that may record the strength and orientation of Earth's magnetic field at the time of their formation. While interpreting these magnetic signatures is challenging due to the complex geological history of these samples, they potentially provide some of the earliest evidence for the existence of Earth's magnetic field during the Hadean Eon. Fluid inclusion studies of ancient zircons have revealed the presence of tiny pockets of fluid that were trapped during crystallization. Analysis of these fluid inclusions provides direct evidence for the composition of fluids that were present during early crustal formation. Some fluid inclusions contain high concentrations of dissolved salts and metals, indicating that the fluids involved in early crustal processes were quite different from modern groundwater or surface water. The phosphorus content of ancient zircons has been used to infer the availability of this essential element during early Earth history. Phosphorus is required for many biological processes, and its availability may have been a limiting factor for the earliest life forms. The phosphorus signatures preserved in ancient zircons suggest that this element was available in the early crustal environment, though its concentration and chemical form may have been quite different from modern conditions. Comparative studies of zircons from different time periods have revealed how Earth's surface environment evolved during the billions of years following the end of the magma ocean phase. The chemical signatures preserved in zircons show a gradual transition from the extreme conditions of the Hadean Eon to the more moderate and stable conditions that characterized later geological periods. This evolutionary sequence provides a detailed record of how Earth's surface environment developed the characteristics that would eventually allow the flourishing of life. The implications of ancient zircon studies extend beyond understanding Earth's early history to informing our search for life on other planets. The conditions recorded by ancient zircons, including the early presence of liquid water and moderate surface temperatures, provide insights into how rapidly planetary surface environments can evolve from extremely hostile to potentially habitable conditions. This information is relevant for understanding the potential habitability of exoplanets and for identifying the types of planetary environments that might be most likely to support the development of life. Recent advances in analytical techniques continue to reveal new information from ancient zircons, and ongoing research is likely to provide additional insights into Earth's early history. Improved mass spectrometry techniques allow for more precise measurements of isotopic compositions, while advances in electron microscopy provide better resolution of internal crystal structures. These technological developments ensure that ancient zircons will continue to provide valuable information about Earth's earliest history for years to come. The preservation of ancient zircons also highlights the importance of protecting geological heritage sites where these remarkable materials can be found. The localities that contain ancient zircons represent irreplaceable archives of Earth's early history, and their protection is essential for continuing research into our planet's origins. The scientific value of these materials extends far beyond their immediate research applications, to include their potential for answering fundamental questions about planetary formation and the conditions necessary for the development of life. The study of ancient zircons represents one of the most direct approaches available for investigating the conditions that existed during Earth's earliest history. While much of the rock record from the Hadean Eon has been destroyed by subsequent geological processes, these tiny mineral time capsules preserve chemical signatures that provide unique insights into the processes that shaped our planet during its formative years. The information preserved in ancient zircons continues to refine our understanding of how Earth evolved from a molten ball of rock into the complex, life-supporting planet we know today. As Earth's magma ocean gradually cooled and solidified, the chemical and physical processes occurring within its depths were setting the stage for one of the most fundamental changes in our planet's history, the formation of the first stable continental masses. The transition from a world dominated by oceanic crust to one with distinct continental and oceanic regions would prove crucial for the long-term evolution of Earth's surface environment and its eventual ability to support complex life. The formation of continental crust during and immediately following the magma ocean period involved processes quite different from those that create continental crust today. Modern continental crust forms primarily through the melting and differentiation of oceanic crust at subduction zones, where oceanic plates sink back into the mantle. However, during the Hadean Eon, plate tectonics as we understand it today had not yet developed, and continental crust formation occurred through different mechanisms related to the cooling and differentiation of the magma ocean itself. The earliest continental crustal materials likely formed through the process of fractional crystallization within the cooling magma ocean. As the molten rock cooled, minerals with higher melting points crystallized first and, being denser than the remaining liquid, sank toward the bottom of the magma ocean. This left behind residual liquids that were progressively enriched in elements that form minerals with lower melting points and lower densities. These evolved liquids, rich in silica, aluminum, and alkali metals, eventually crystallized to form rocks with compositions similar to modern continental crust. The accumulation of these low-density, silica-rich materials at or near the surface of the cooling magma ocean created the first protocontinental masses. Unlike modern continental crust, which is typically 30 to 50 kilometers thick, these early continental materials may have been much thinner, perhaps only a few kilometers thick initially. However, they represented the first stable landmasses on Earth's surface, providing elevated areas that would remain above sea level even as the first oceans began to form. The chemical composition of these early continental materials was probably somewhat different from modern continental crust. The extreme temperatures and pressures that characterize the magma ocean environment, combined with the unique chemical conditions of the early Earth, led to the formation of mineral assemblages that are rare or absent in modern rocks. Some of these early continental rocks may have been dominated by minerals that require very high temperatures to form, creating rock types that have no direct modern analogues. The process of continental crust formation was not uniform across Earth's surface, but was likely concentrated in areas where local conditions favored the accumulation and preservation of low-density materials. Regions with particularly thick accumulations of fractional crystallization products, or areas where convective upwelling brought silica-rich materials to the surface, may have become the sites of the first substantial continental masses. The role of impact cratering in early continental crust formation may have been more significant than previously recognized. Large asteroid and comet impacts during the late heavy bombardment created enormous crater structures that disrupted the normal crystallization processes of the cooling magma ocean. These impacts generated complex patterns of melting, mixing, and differentiation that could have enhanced the formation of chemically evolved continental-type rocks in and around the impact sites. The heat generated by large impacts was sufficient to create extensive zones of melting that persisted for thousands of years after each impact event. Within these impact-generated melt zones, fractional crystallization and chemical differentiation could proceed under somewhat different conditions than in the undisturbed magma ocean, potentially leading to the formation of more highly evolved rock compositions. Some of the earliest continental crustal materials may have formed within these impact-modified environments. The gravitational effects of large impact craters may also have influenced the patterns of convection and material transport within the cooling magma ocean. Impact craters created topographic depressions that could focus convective upwelling, bringing material from greater depths to the surface. This enhanced vertical transport could have accelerated the processes of chemical differentiation and continental crust formation in the vicinity of large impact structures. The formation of the first continental masses had important implications for the early development of Earth's hydrological cycle. Continental areas provided elevated terrain that influenced atmospheric circulation patterns and created opportunities for the formation of the first river systems as surface water began to accumulate. The chemical weathering of early continental rocks by acidic rainfall contributed to the chemical evolution of the early oceans and helped to establish some of the biogeochemical cycles that would later prove essential for life. The early continental masses also provided the first opportunities for the formation of sedimentary rocks through the weathering and erosion of primary crustal materials. The physical and chemical breakdown of early continental rocks created the first sedimentary particles, which were transported by wind and water to accumulate in low-lying areas. These early sedimentary deposits, while quite different from modern sedimentary rocks, represented the beginning of the sedimentary rock cycle that continues to operate today. The thermal insulation provided by early continental masses may have influenced the cooling rate of the underlying mantle and the longevity of magmatic processes in the early crust. Thick continental crust acts as an insulating blanket, slowing the loss of heat from the interior and potentially maintaining higher temperatures at depth for extended periods. This thermal effect could have prolonged volcanic activity and enhanced the chemical differentiation processes that contributed to continental crust formation. The development of early continental masses also created the first significant topographic relief on Earth's surface. While the earliest continental areas were probably relatively low-lying compared to modern mountain ranges, they nonetheless provided elevated terrain that contrasted with the surrounding oceanic areas. This topographic relief influenced atmospheric circulation, precipitation patterns, and the development of early drainage systems. The chemical stability of early continental materials was enhanced by their low-density compositions, which made them resistant to recycling back into the mantle through convective processes. Unlike the denser oceanic crustal materials, which could be easily carried downward by convective currents in the still hot mantle, the lighter continental materials tended to remain at or near the surface. This buoyancy effect was crucial for the preservation of continental crust through the violent early stages of Earth's history. The formation of early continental crust also established important reservoirs for radioactive elements such as uranium, thorium, and potassium. These elements are concentrated in continental crustal rocks relative to oceanic crust and mantle rocks, and their radioactive decay provides a significant source of heat for the continental crust. The concentration of radioactive elements in early continental masses helped to maintain elevated temperatures within the continental crust and may have enhanced the processes of crustal melting and differentiation. The magnetic properties of early continental materials may have been different from those of modern continental rocks due to the unique conditions under which they formed. The high temperatures and reducing chemical conditions that characterized the early Earth environment could have affected the formation and preservation of magnetic minerals within the early continental crust. Understanding these magnetic properties is important for interpreting paleomagnetic records from the earliest continental rocks. The interaction between early continental masses and the developing atmosphere had important implications for the chemical evolution of both systems. Continental rocks provided new types of surfaces for atmospheric chemical reactions, and the weathering of continental materials contributed new chemical species to the atmosphere. The formation of soils and regoliths on early continental surfaces created additional opportunities for atmospheric surface interactions. The early continental masses also provided the first opportunities for the formation of freshwater bodies as distinct from the developing oceanic system. Rivers, lakes, and groundwater systems associated with early continental areas created new chemical environments with different compositions and properties from seawater. These freshwater systems may have provided important chemical and physical environments for the eventual development of life. The erosional processes that affected early continental masses were quite different from modern continental erosion due to the absence of vegetation and the different atmospheric and climatic conditions that characterize the early Earth. Without plant cover to protect the surface, early continental rocks were subject to intense physical and chemical weathering that may have proceeded at rates much higher than modern continental erosion rates. This enhanced weathering contributed to the rapid chemical evolution of the early surface environment. The formation of early continental crust required the operation of efficient mechanisms for concentrating incompatible elements, those that are excluded from common mantle minerals and tend to become concentrated in crustal rocks. The magma ocean environment provided ideal conditions for this concentration process, as the extensive melting and fractional crystallization that characterized this period created numerous opportunities for incompatible elements to become separated from compatible elements and concentrated in residual liquids. The trace element signatures preserved in the oldest continental crustal rocks provide evidence for the processes that were responsible for their formation. These signatures show enrichments in elements such as potassium, rubidium, and barium that are characteristic of highly evolved magmatic processes. The specific patterns of trace element enrichment and depletion provide insights into the degree of fractional crystallization and the types of mineral phases that were involved in early continental crust formation. The isotopic compositions of early continental crustal rocks provide additional constraints on their formation mechanisms and source materials. Neodymium and strontium isotope ratios in ancient crustal rocks indicate that their source materials had undergone chemical differentiation for extended periods before the final crystallization that created the preserved crustal rocks. This evidence supports models that invoke prolonged fractional crystallization processes within the cooling magma ocean. The lead isotope compositions of early continental rocks provide information about the timing and duration of the processes that created them. Lead isotopes are produced by the radioactive decay of uranium and thorium, and the accumulated lead in ancient rocks provides information about how long these elements had been present in crustal reservoirs. The lead isotope signatures of the oldest continental rocks indicate that crustal differentiation processes began very early in Earth's history, possibly during the final stages of planetary accretion. The preservation of early continental crustal materials through billions of years of subsequent geological activity required that they be incorporated into stable tectonic environments where they could avoid destruction by later geological processes. The oldest preserved continental rocks are found in areas known as cratons, stable continental regions that have remained largely undeformed since their formation. The existence of these ancient cratons provides evidence that stable continental masses had formed by the end of the Hadean Eon. The study of the oldest continental rocks has revealed that they contain mineral assemblages that formed under pressure and temperature conditions, consistent with depths of 30 to 50 kilometers below the surface. This evidence indicates that substantial thicknesses of continental crust had formed by the time these rocks crystallized, suggesting that the processes of continental crust formation were highly efficient during the early Earth period. The water content of early continental crustal rocks, as indicated by the presence of hydrous minerals such as amphibole and biotite, provides evidence that water was available during continental crust formation processes. The incorporation of water into continental crustal minerals had important effects on the physical and chemical properties of these rocks, including their melting behavior and their susceptibility to weathering and alteration. The formation of early continental crust also had important implications for the development of Earth's early climate system. Continental masses provided different surface properties compared to oceanic areas, with different albedos, thermal capacities, and roughness characteristics that influenced atmospheric circulation and precipitation patterns. The presence of continental areas may have enhanced the efficiency of atmospheric heat transport and contributed to the moderation of early Earth's climate. The chemical weathering of early continental rocks contributed important chemical species to the early oceans and atmosphere, including nutrients that would later prove essential for biological processes. The weathering of continental silicate rocks consumed carbon dioxide from the atmosphere, providing an important mechanism for regulating atmospheric greenhouse gas concentrations. This early continental weathering may have played a crucial role in maintaining surface temperatures within the range necessary for liquid water stability. The formation of the first substantial continental masses during the late Hadean and early Archean eons marked a fundamental transition in Earth's surface evolution. These early continents provided stable platforms for the accumulation of sedimentary rocks, the development of complex surface environments, and eventually the establishment of the first ecosystems. The processes that created these early continental masses established patterns of crustal formation and preservation that continue to influence Earth's surface evolution today. As the Great Magma Ocean continued its inexorable cooling, the establishment of a stable thermal regime became one of the most critical factors governing Earth's transition from a molten world to one capable of supporting surface water and eventually life. The thermal evolution during this period was controlled by a complex interplay of heat sources and heat loss mechanisms that operated on timescales of millions of years. The primary heat sources maintaining the magma ocean's elevated temperatures included the ongoing decay of radioactive isotopes, the gradual release of gravitational potential energy as dense materials settled toward the planet's center, and the continued input of kinetic energy from asteroid and comet impacts. During the peak of the magma ocean period, these heat sources were sufficient to maintain surface temperatures well above the melting point of rock. But as time progressed, their relative importance began to change. Radioactive decay was perhaps the most steady and predictable of these heat sources. Elements such as uranium-238, thorium-232, and potassium-40, with their extremely long half-lives, provided a continuous source of thermal energy that would persist for billions of years. However, during the Hadean eon, short-lived radioactive isotopes also played important roles. Aluminum-26, with a half-life of only 720,000 years, was much more abundant in the early solar system than it is today, and provided significant heating during the first few million years of planetary formation. The heat generated by radioactive decay was not uniformly distributed throughout the planet, but was concentrated in regions where radioactive elements had become concentrated during the differentiation process. The early continental crustal materials, being enriched in these radioactive elements, generated more heat per unit volume than the denser materials that had settled into the mantle and core. This uneven distribution of heat sources created thermal gradients that would influence convection patterns and cooling rates in different parts of the planet. The gravitational energy released during core formation represented another major heat source during the magma ocean period. As droplets of molten iron and nickel descended through the silicate magma toward the planet's center, they released gravitational potential energy that was converted to thermal energy. This process was most intense during the early stages of planetary assembly, when the largest amounts of metallic material were settling out of the magma ocean, but it continued at decreasing rates for millions of years as the final traces of iron were extracted from the silicate portions of the planet. The impact heating from continuing asteroid and comet bombardment provided an external heat source that varied dramatically over time. During the most intense phases of bombardment, large impacts could deliver enough energy to temporarily halt or even reverse the cooling process in localized regions. The largest impacts were capable of remelting portions of the surface that had already begun to solidify, creating temporary pools of molten rock that would persist for thousands of years before cooling again. Against these heat sources, the primary mechanism for heat loss was radiation to space from the planet's hot surface. The rate of radiative heat loss depends strongly on temperature, with hotter surfaces radiating energy much more efficiently than cooler ones. During the peak of the magma ocean period, when surface temperatures exceeded 2000 degrees Celsius, the rate of heat loss to space was enormous, but it was still insufficient to overcome the heat input from the various sources described above. The thick atmosphere that surrounded the molten planet played a crucial role in regulating the cooling process. This dense envelope of rock vapor, water vapor, carbon dioxide, and other gases acted as an insulating blanket that trapped heat radiated from the surface and slowed the overall cooling rate. The greenhouse effect created by this atmosphere was far more intense than anything experienced on Earth today, with atmospheric pressures possibly exceeding 100 times the current atmospheric pressure. As the magma ocean began to cool, the composition and density of the atmosphere gradually changed. Rock vapor, which had been a major component of the early atmosphere, began to condense as temperatures dropped below the vaporization points of various minerals. This condensation reduced the atmospheric pressure and allowed more efficient heat loss to space, creating a positive feedback effect that accelerated the cooling process. The condensation of atmospheric components was not uniform across all chemical species. Different types of rock vapor condensed at different temperatures, creating a sequence of atmospheric evolution as cooling progressed. Silicon and aluminum compounds were among the first to condense, followed by iron and magnesium compounds, and finally by more volatile species such as water vapor and carbon dioxide. This sequential condensation created a stratified atmosphere with different compositions at different altitudes. The formation of the first solid materials at the surface marked a critical transition in the thermal evolution of the planet. Solid rock, even at very high temperatures, conducts heat much less efficiently than convecting liquid rock. The formation of even thin, solid crusts at the surface created an additional thermal barrier that helped to insulate the interior and slow the cooling process. However, these early solid layers were unstable and were frequently disrupted by continued convective motion in the underlying magma ocean. The thermal conductivity of the early solid materials was influenced by their chemical composition, crystal structure, and porosity. The high-temperature minerals that formed first from the cooling magma ocean had different thermal properties than the lower-temperature minerals that formed later. These variations in thermal conductivity created complex patterns of heat flow that influenced where and how quickly different regions of the surface would solidify. The role of water in the thermal evolution process was particularly complex and important. Water has a very high heat capacity, meaning that it can absorb large amounts of thermal energy, with relatively small changes in temperature. The presence of dissolved water in the magma ocean would have significantly affected its cooling rate, generally slowing the process by increasing the total amount of heat that needed to be removed for solidification to occur. Water also affects the melting temperature of silicate rocks, generally lowering the temperature at which crystallization begins. This means that magmas containing dissolved water would begin to solidify at lower temperatures than dry magmas of similar composition. The water content of the magma ocean therefore had a direct influence on the temperature at which the first solid materials would begin to form at the surface. The solubility of water in molten silicate rock increases with pressure, meaning that the deeper portions of the magma ocean could dissolve more water than the shallower regions. As the magma ocean cooled and crystallized, this dissolved water was gradually released, contributing to the growing atmospheric inventory of water vapor. The timing and rate of this water release had important implications for the development of the early atmosphere and the eventual formation of the first oceans. The convection patterns within the cooling magma ocean played a crucial role in determining the overall cooling rate and the spatial patterns of solidification. Vigorous convection helped to transport heat efficiently from the deep interior to the surface, where it could be radiated away to space. However, convection also helped to maintain uniform temperatures throughout the magma ocean, preventing the formation of stable temperature gradients that might allow preferential cooling in certain regions. As the magma ocean cooled and its viscosity increased, the efficiency of convective heat transport gradually decreased. Higher viscosity magmas convect more slowly and less efficiently than low viscosity magmas, creating a negative feedback effect that further slowed the cooling process. This change in convection efficiency was particularly important during the later stages of magma ocean evolution, when the remaining liquid had become highly evolved and viscous due to fractional crystallization. The crystallization process itself generated additional complexity in the thermal evolution. The formation of solid crystals from liquid magma releases latent heat, similar to the way that freezing water releases heat. This latent heat release helped to maintain elevated temperatures during the crystallization process and slowed the overall cooling rate. The amount of latent heat released depended on the types and quantities of minerals crystallizing, with some mineral phases releasing more heat than others. The settling of dense crystalline materials toward the bottom of the magma ocean created additional thermal effects. The gravitational energy released as these materials sank was converted to heat, providing a continuing internal heat source even as the surface was cooling. This process was most significant during the early stages of crystallization, when large volumes of dense minerals were forming and settling rapidly. The thermal evolution of different regions of the magma ocean was influenced by local variations in composition, depth, and heat sources. Areas with higher concentrations of radioactive elements experienced more internal heating and cooled more slowly than regions with lower radioactive element concentrations. Similarly, regions with thicker accumulations of insulating solid material retained heat longer than areas where the magma ocean remained in direct contact with the atmosphere. The transition from a fully liquid magma ocean to one with substantial amounts of solid material created new thermal regimes that had not existed earlier in Earth's history. The coexistence of solid and liquid phases created opportunities for thermal gradients to develop and persist, allowing different parts of the system to exist at different temperatures simultaneously. This thermal stratification would prove important for the later development of more complex geological processes. The cooling rate of the magma ocean was not constant over time, but varied significantly depending on the changing balance between heat sources and heat sinks. During the early stages, when heat input from impacts and radioactive decay was high and atmospheric insulation was most effective, cooling rates were relatively slow. As these factors changed over time, cooling rates accelerated, leading to more rapid solidification during the later stages of magma ocean evolution. The development of thermal boundary layers at the interface between solid and liquid regions created additional complexity in the cooling process. These boundary layers, where temperature changed rapidly over short distances, became sites of enhanced heat transfer and often controlled the overall rate of solidification. The physics of heat transfer across these boundary layers was influenced by factors such as the roughness of the solid-liquid interface and the vigor of convective motion in the liquid regions. The role of volatile compounds in the thermal evolution extended beyond their direct effects on melting temperatures and heat capacity. The escape of gases from the magma ocean created additional pathways for heat loss, as the hot gases carried thermal energy with them as they rose through the atmosphere and eventually escaped to space. This process, known as advective heat loss, became increasingly important as the atmospheric pressure decreased during cooling. The formation of the first stable crustal materials marked a fundamental change in the thermal regime at Earth's surface. Unlike the constantly convecting magma ocean, solid crustal rocks could support temperature gradients and create thermal boundary layers that persisted for extended periods. This change allowed for the development of more complex thermal structures that would later prove important for volcanic processes and crustal evolution. The thermal evolution during the late stages of magma ocean cooling was complicated by the onset of volcanic processes as solid crust began to form. Volcanic eruptions provided new mechanisms for heat transport from the interior to the surface, creating localized zones of high heat flow that contrasted with the generally cooling surface environment. These volcanic systems also created new pathways for the release of dissolved gases and the transport of chemical species from depth to the surface. The establishment of a stable geothermal gradient, where temperature increases predictably with depth below the surface, represented the final stage in the thermal evolution of the magma ocean period. This gradient, which is still present in Earth's crust today, reflects the balance between heat generation from radioactive decay in the crust and mantle and heat loss through conduction to the surface. The establishment of this stable thermal structure marked the end of the chaotic thermal conditions that had characterized the magma ocean period. The cooling timescales for different aspects of the magma ocean evolution varied dramatically depending on the specific processes involved. The surface could cool from molten conditions to temperatures allowing liquid water in perhaps a few million years under favorable conditions, while the deep interior remained partially molten for tens of millions of years or longer. These different timescales created a complex sequence of thermal evolution that unfolded over extended periods. The thermal legacy of the magma ocean period persisted long after the surface had solidified and oceans had formed. The differentiated structure created during this period, with its concentration of radioactive elements in the crust and the efficient thermal insulation provided by the solid surface layers, established thermal patterns that continue to influence Earth's internal dynamics today. The heat flow patterns established during the magma ocean period helped to determine where volcanic activity would be concentrated and how the early crustal blocks would evolve. Modern estimates of the duration of the magma ocean period range from several million to several tens of millions of years, depending on the specific assumptions made about atmospheric composition, impact rates, and internal heat sources. These estimates are based on sophisticated computer models that attempt to capture the complex interactions between all the various thermal processes that were operating during this period. While there remains uncertainty about the exact timescales involved, all models agree that the thermal evolution was a gradual process that unfolded over geological time periods. The study of thermal evolution during the magma ocean period has important implications for understanding similar processes on other planets. Mars, Venus, and the Moon all show evidence of having experienced magma ocean phases during their early histories, and comparative studies of these bodies help to refine our understanding of the thermal processes that operated on early Earth. The different evolutionary paths followed by these bodies highlight the importance of factors such as planetary size, distance from the Sun, and atmospheric composition in determining thermal evolution. The thermal conditions that characterize the magma ocean period created unique opportunities for chemical and physical processes that cannot occur under modern Earth conditions. The combination of extremely high temperatures, reducing atmospheric conditions, and the presence of vast quantities of molten rock created an environment where unusual mineral phases could form and where chemical reactions could proceed along pathways that are not available today. Understanding these ancient thermal conditions is therefore crucial for interpreting the chemical and physical evidence preserved in the oldest rocks and minerals. As Earth's thermal evolution progressed and surface conditions began to moderate, the stage was set for one of the most remarkable transitions in planetary history, the condensation of water vapor from the cooling atmosphere to form the first liquid oceans. This transition represented not just a physical change of state, but a fundamental transformation in the character of Earth's surface environment that would make possible all the complex geological and biological processes that followed. The formation of Earth's first oceans was not a sudden event, but rather a gradual process that unfolded over millions of years as surface temperatures slowly dropped below the critical threshold for water vapor condensation. The timing of this transition was controlled by the complex interplay between atmospheric composition, surface temperature, and atmospheric pressure, all of which were evolving simultaneously as the planet continued to cool from its molten state. The water that would eventually form the first oceans had multiple sources, each contributing to the growing atmospheric inventory of water vapor during the magma ocean period. Outgassing from the cooling magma ocean itself provided a major source, as water that had been dissolved in the molten rock was released as the temperature dropped and crystallization proceeded. This process was similar to the way carbonated beverages release dissolved carbon dioxide when opened, but operating on a planetary scale over millions of years. Cometary impacts during the late heavy bombardment contributed additional water to the atmospheric reservoir. Comets, often described as dirty snowballs, contained substantial amounts of water ice along with other volatile compounds such as carbon dioxide, methane, and ammonia. When these icy bodies collided with Earth at velocities of tens of kilometers per second, the water they contained was instantly vaporized and added to the growing atmospheric inventory. Asteroids, particularly those originating from the outer regions of the asteroid belt, also contained significant amounts of water locked up in hydrated minerals. When these water-bearing asteroids impacted the early Earth, the shock heating from the collision released this bound water as vapor, contributing to the atmospheric water budget. The relative importance of different water sources remains an active area of research, with isotopic studies of Earth's water providing clues about the origins of our planet's hydrosphere. The atmospheric pressure during the late magma ocean period was crucial for determining when liquid water could first become stable at Earth's surface. Water can only exist as a liquid within a specific range of temperature and pressure conditions, and the extremely high atmospheric pressures that characterized the early Earth allowed liquid water to remain stable at temperatures well above its normal boiling point of 100 degrees Celsius. As the atmosphere gradually cooled and atmospheric pressure decreased through the condensation of rock vapor and the escape of gases to space, the conditions for liquid water stability evolved continuously. The first liquid water may have formed at temperatures of several hundred degrees Celsius under the high-pressure conditions of the early atmosphere, creating a hot, dense fluid quite unlike the cool oceans we know today. The initial condensation of water vapor likely occurred preferentially in regions where surface temperatures had dropped below the local condensation point, which varied with altitude, atmospheric composition, and local pressure conditions. Low-lying areas, such as impact crater basins and topographic depressions between early crustal blocks, would have been among the first places where liquid water could accumulate and persist. The chemistry of this early condensed water was radically different from modern rainwater or seawater. The water vapor in the early atmosphere had equilibrated with a complex mixture of volcanic gases, rock vapor, and impact-derived materials, creating condensate with high concentrations of dissolved metals, acids, and other chemical species. The first raindrops would have been highly acidic solutions capable of aggressively attacking any solid rocks they contacted. The interaction between this acidic early precipitation and the newly formed crustal rocks initiated the first chemical weathering processes on Earth's surface. Unlike modern weathering, which operates at relatively low temperatures and in the presence of atmospheric oxygen, early weathering occurred at very high temperatures under strongly reducing conditions. These extreme weathering conditions created unusual chemical products and mineral assemblages that have no direct modern analogues. The accumulation of liquid water in surface depressions was initially unstable, with repeated cycles of evaporation and condensation as surface temperatures fluctuated, and volcanic activity periodically raised local temperatures above the boiling point. These early water bodies were temporary features that appeared and disappeared as environmental conditions changed, but they represented the first steps toward the establishment of stable surface hydrosphere. The salinity of the early water bodies increased rapidly as evaporation concentrated dissolved materials and continued weathering added new chemical species to the water. The high temperatures that characterized the early surface environment enhanced the solubility of many minerals, allowing the early water bodies to achieve salt concentrations far exceeding those of modern seawater. Some of these early brines may have been so concentrated that they more closely resembled hot chemical solutions than natural water bodies. The thermal properties of these hot, concentrated brines were quite different from those of pure water or modern seawater. The high dissolved salt content raised the boiling point and lowered the freezing point of the solutions, helping to maintain liquid water over a broader range of temperature conditions. The high temperature also reduced the density and viscosity of the water, affecting circulation patterns and the efficiency of heat transport within the early water bodies. As surface temperatures continued to decline and atmospheric pressure stabilized at lower levels, the early water bodies gradually became larger, more stable, and more interconnected. The formation of the first river systems began as elevated areas shed water toward lower-lying basins, creating networks of surface water flow that helped to distribute water across broader areas of the surface. These early river systems were quite different from modern rivers in both their physical characteristics and their chemical properties. The hot, acidic water was capable of extremely rapid erosion of the early crustal rocks, carving channels and valleys at rates far exceeding those of modern river systems. The high dissolved mineral content also affected the density and flow characteristics of the water, creating unique hydraulic conditions that have no modern parallels. The sedimentary processes associated with these early aquatic systems began to create the first water-laid sedimentary deposits on Earth's surface. The rapid chemical and physical weathering of crustal rocks produced large volumes of sedimentary particles that were transported by the hot, turbulent early rivers and deposited in the growing water bodies. These early sediments had unusual compositions, reflecting the extreme weathering conditions and the unique chemistry of the early surface environment. The evaporation of water from these early surface bodies created the first evaporate mineral deposits as dissolved salts reached saturation and precipitated from solution. The high temperatures and unusual chemical compositions of the early brines led to the formation of evaporate mineral assemblages, quite different from those found in modern evaporative environments. Some of these early evaporate minerals are now extinct and can only be inferred from theoretical studies of high-temperature brine chemistry. The establishment of a stable hydrological cycle, with evaporation from surface water bodies, atmospheric transport of water vapor, and precipitation over land areas, represented a major milestone in Earth's surface evolution. This cycle created mechanisms for the global transport of water and dissolved chemical species, helping to homogenize surface conditions and establish chemical equilibria between different parts of the surface system. The thermal regulation provided by the early hydrological cycle helped to moderate surface temperature variations and create more stable environmental conditions. The high heat capacity of water meant that large water bodies could absorb and store thermal energy during warm periods and release it during cooler periods, creating a thermal buffering effect that reduced temperature extremes. The chemical evolution of the early oceans was driven by the continuous input of dissolved materials from weathering processes and volcanic outgassing, balanced by the removal of materials through precipitation of minerals and escape of gases to the atmosphere. This dynamic chemical system gradually evolved toward compositions that were more similar to modern seawater, though the process required hundreds of millions of years to complete. The development of circulation patterns within the early oceans was controlled by temperature gradients, density differences, and the effects of atmospheric winds on the water surface. Without continents to create barriers to oceanic circulation, the early oceans may have had simpler circulation patterns than modern oceans, but the extreme temperature gradients and unusual water chemistry created unique circulation dynamics. The interaction between the early oceans and the cooling atmosphere created new mechanisms for atmospheric chemical evolution. The dissolution of atmospheric gases in seawater removed these species from the atmosphere, while evaporation and chemical reactions at the sea surface added new species to the atmospheric inventory. This ocean-atmosphere chemical exchange became an important factor controlling the composition of both systems. The formation of sea ice was unlikely during the early stages of ocean development due to the high temperatures and salt concentrations that characterized the early seawater. However, as conditions gradually moderated, the first formation of solid ice may have occurred in polar regions or at high altitudes, creating new physical and chemical environments at Earth's surface. The biological implications of early ocean formation were profound, though life itself had not yet appeared on Earth. The establishment of stable liquid water bodies created the chemical and physical environments that would later prove essential for the origin and evolution of life. The concentration mechanisms operating in early evaporative environments may have been crucial for concentrating organic compounds to levels sufficient for the first biochemical processes. The trace element chemistry of the early oceans was controlled by the weathering of early crustal rocks and the input of materials from volcanic and impact sources. The unusual compositions of these early crustal materials, combined with the extreme weathering conditions, created trace element signatures in early seawater that were quite different from modern ocean chemistry. These ancient chemical signatures are sometimes preserved in very old sedimentary rocks and provide important clues about early ocean conditions. The pH of the early oceans was likely quite different from modern seawater due to the different atmospheric composition and the products of high-temperature rock weathering. The early atmosphere contained little or no free oxygen, but substantial amounts of carbon dioxide and other acidic gases, creating acidic precipitation that would have lowered ocean pH. However, the weathering of crustal rocks also released alkaline materials that could neutralize acidity, creating a complex pH evolution over time. The formation of the first ocean basins was controlled by the topography created during crustal formation and impact cratering. Unlike modern ocean basins, which are created and destroyed by plate tectonic processes, the early ocean basins were probably more permanent features controlled by the primordial topography of the cooling planet. These early basins may have been deeper relative to their size than modern ocean basins due to the different crustal formation mechanisms operating during the Hadean Eon. The thermal structure of the early oceans was quite different from modern oceans due to the high surface temperatures and the different heat sources operating during this period. Volcanic heating from the seafloor was probably much more intense than today due to the higher heat flow from the still cooling interior. This heating created strong thermal gradients within the early oceans and may have driven vigorous circulation patterns. The seasonal and daily temperature variations in the early oceans were probably quite different from modern patterns due to the different atmospheric composition, the lack of continents to create land-sea temperature contrasts, and the different solar radiation patterns. The early Earth's faster rotation rate, with days lasting only about 5 hours, would have created different patterns of heating and cooling that affected ocean temperatures and circulation. The chemical precipitation processes operating in the early oceans were enhanced by the high temperatures and unusual chemical compositions that characterize these water bodies. The formation of chemical sediments through direct precipitation from seawater was probably much more important during the early Earth period than it is today, creating unusual sedimentary rock types that are rare in the modern geological record. The early oceans also served as important reservoirs for atmospheric gases, with the solubility of different gases depending on temperature, pressure, and water chemistry. The early oceans may have contained much higher concentrations of dissolved carbon dioxide than modern seawater due to the higher atmospheric carbon dioxide levels and the different ocean chemistry. This dissolved carbon dioxide would later prove important for early biological processes. As the early oceans continued to evolve and mature, they gradually developed the physical and chemical characteristics that would make them suitable for the eventual development of life. While this transition required hundreds of millions of years to complete, the formation of stable liquid water bodies during the late Hadean Eon represented one of the most important steps in Earth's evolution from a sterile, molten world to a planet capable of supporting the complex chemistry of life. The establishment of Earth's early oceans marked not just the end of the magma ocean period, but the beginning of a new chapter in planetary evolution, where liquid water would play a central role in shaping surface processes, chemical cycles, and eventually the development of life itself. The transition from a world of molten rock to one of liquid water represented one of the most profound transformations in Earth's history, setting the stage for all the remarkable developments that would follow in the billions of years ahead. From that ancient ocean of fire emerged the world we know today. The churning seas of molten rock that once covered our entire planet have given way to solid continents and liquid oceans, to an atmosphere that can sustain life and a magnetic field that shields us from the harsh radiation of space. Every mountain range, every grain of sand, every drop of water in our modern world carries within it the memory of those primordial flames that forged our planet during its earliest days. The story of Earth's magma ocean reminds us that even the most violent beginnings can lead to the most beautiful outcomes, and that our peaceful blue world was born from the most extraordinary transformation in planetary history.